welcome everyone to our webinar today in the Marine and Coastal Science community, assessing the effect of offshore wind farms and climate change in the North Sea. Today we're joined by Dr Michela De Dominicis, who is a senior scientist at the National Oceanography Centre. She's a physical oceanographer with over 15 years expertise in marine numerical modelling. Her broad research interests are around human-ocean connections, and as part of her work, she uses ocean computer simulations to understand how the ocean will change in future decades under different what-if scenarios, investigating the impact of offshore renewable energy devices, as well as the response of coastal areas to extreme weather and sea level rise. Today's webinar will explore the impact of expanding offshore wind farms into deeper waters, where there is the potential for them to perturb the natural ocean mixing. As always, there will be the chance for questions at the end of the presentation, so please submit these in the Q&A option at the bottom of your screen at any point during the presentation, and then at the end I'll be able to ask those on your behalf. So thanks again for logging in, and I will now hand over to Michela for the presentation.
Hello, thank you, Hemi, for the introduction, and thank you for joining the seminar. Yes, so I'm Michela De Dominicis, I work at the National Oceanography Centre, and this work is part of a project that is called Pelagio. So I'm going to present some of my work, but some of it is done by the Pelagio project people. So the main topic here is assessing the effects of offshore wind farms and climate change in the North Sea. But before going to the seminar, I would like to introduce myself and my research interests. So my research mainly explores how the ocean and human activities interact. And to do this, I use ocean model computer simulations. And I study different topics. One is the impacts of offshore renewable energy, like underwater tidal turbines or wind turbines, which is the topic of this presentation, and that was part of the Pelagio project. But I also study the impacts of climate change on coastal areas, so the impacts of extreme storms and sea level rise in coastal areas, and this is part of another project that is called CHAMFE. But more in general, in NOC, I lead on the development of two high-resolution coastal ocean models. High resolution in this case means less than 1 kilometer, actually around 500 meters close to the coast. One system is called UK 500 and is mainly is being developed basically during the last couple of years, and is mainly for predicting coastal flooding around all around the UK. And the other system instead is called the Scottish Shelf model, and is the system that I will talk about a lot during this seminar. So it's called the Scottish Shelf model, but actually covers the entire Northwest European continental shelf. And it has a variable resolution. It's pretty low at the boundaries of the model, but then it's high close to the coast. And then it has some nested models in Scottish waters. And this system was built for the Scottish government, and it has been under development for the last 10 years, more than 10 years. So this was just to give you an introduction about myself and about the modeling systems that I use and develop. Let's go into the topic for today. So, as you might know, the UK is committed to delivering up to 50 gigawatts of offshore wind by 2030, including up to 5 gigawatts of floating wind. And the reason why we are doing some research is because the physical and biogeochemical footprint of such large-scale expansion of offshore wind infrastructure into deeper waters and under the influence of climate change is unknown. So basically the question that I like to answer is how will such large-scale deployment of offshore wind turbines will impact our seas. And this is important because in order to, we want to govern the environment in a way that we are balancing the renewable energy expansion with the ecosystem protection and also with the development of other human activities like fisheries and shipping. So a bit of an introduction around the North Sea. The North Sea is a shelf sea, so I'm not sure about the background of the people attending the seminar, so apologies if it is too simple or too complicated, but I will try to explain a bit of the ocean dynamics in the shelf seas. So there are different processes that are acting. You have the freshwater input from the rivers, tides, winds, and then the seasonal variability, so the different season and the different heating coming from the atmosphere. And then there is the exchange with an open ocean. But the process I'm going to focus in this presentation is the stratification of the water column. So the North Sea is a shelf sea, which means it's not very deep. It's around 200 meters deep, and during winter is completely mixed. This means that the water that is on the bottom can go on the top, and the water that is on the top can go on the bottom. And this movement of water is driven by the tides and by the winds. During summer, instead, the North Sea is seasonally stratified, not everywhere, not in coastal areas, but the deeper areas are seasonally stratified. And this happens because the heating coming from the atmosphere makes the water at the surface warmer and lighter. And so we have two-layer system. That is what you see in this figure. So you have lighter water on the top and colder and denser water on the bottom. And this is a stratified sea, and this happens only during the summer months. But this is very important because the movement of water basically drives the movement of phytoplankton, zooplankton, and those are the nutrients, and those are the basis of the food web for fish, then seabirds, marine mammals. So if we change something in the movement of phytoplankton, for example, then this can have cascading effects on fish or seabirds or marine mammals. We don't know, and it's something that we want to explore. So this is basically what I was introducing now, is that if we put an offshore wind farm at sea, potentially we can perturbate the movement of phytoplankton, zooplankton, and then we can affect fish, birds, and marine mammals. So this was not a problem in the past because offshore wind farms in the past were mainly built in coastal areas, and coastal areas are always mixed because of the effect of the tides, which are stronger. So coastal areas are always mixed, and we didn't have this problem. But right now, the offshore wind industry is moving into deeper waters where stronger winds are available, and moving also from having monopile structures for the wind farms into having floating structures that are anchored at the seabed. So we want to understand if a massive expansion of offshore wind farms can perturbate the natural equilibrium in between mixing and stratification. And it's mainly a problem of scale. So if we have one wind turbine, probably it's not really going to matter. But since the plan for the next 25 years is to have a massive expansion, so thousands of wind turbines. We want to understand what are the cumulative effects of having so many wind turbines at sea, and also trying to understand what are the best locations where to place them without harming the marine environment or other human activities. In Pelagium, which is a project that is part of a bigger program that is called EcoWind, which is funded by NERC, we are using models at different scales to try to understand what are the impact of offshore wind farms. In this presentation, I will mainly focus on the shelf-wide scale, on the shelf-wide scale, which is the model that I introduced before. But in the project, we are looking also at the local scale and the regional scale. But I'm mainly interested in understanding the cumulative impacts of offshore wind farms everywhere in the North Sea. That's why we are using the shelf-wide model. So we are using a combination of actually 3 different models. One is called FECOM, which is an hydrodynamic model. Then we have GOTEM, which is a turbulence model, and then we have ERTSEM, that is a biogeochemical model. So FECOM, the ocean model, provides us information about temperature, salinity, currents. The turbulence model gives us information around turbulence, turbulent kinetic energy, and all this information is then transferred to ERTSEM, which is the biogeochemical model. And then ERTSEM can provide us information about the movement of nutrients, phytoplankton, zooplankton, oxygen, chlorophyll A. And those are all important. Sorry, these are all. What we want to understand is then how introducing the wind farms can change the distribution of different parameters from the physics to the biogeochemistry. And this is just an example provided by my colleague Gianni Jardin, which works at NUC, and she's also involved in the Pelagio project. These are some examples of the model outputs. These are movies of the nitrate distribution during a few days and phytoplankton distribution. And these are just baseline conditions. And we want to understand how something like this will change with a massive expansion of offshore wind farms. Unfortunately, we are running the models now, so I cannot show you some results about this yet, but maybe in the future. So as I said, we have this modeling system composed by 3 models, an ocean model, a turbulence model, and a biogeochemical model. And we have modified those models to introduce the effect of the offshore wind farms. And this is done using 2 different parameterization. One is to reproduce the effect of the wind wake, which is the wind speed deficit acceleration in the wake of the offshore wind farm when the offshore wind farm is operating. And the other parameterization, which is embedded in the ocean model now and in the turbulence model, it is built to reproduce the drag of the underwater structure and consequent mixing, and which is generated by in the wake of the offshore wind farm. And the good thing that we tried to do in Pelagio was to validate the results of our model with some observations that we have taken in the vicinity of a wind farm in 2023 and 2024. And this is to get some confidence in our model results and then to be able to use them to predict the effect of offshore wind farms in other locations where we cannot collect observations. I hope now I'm not going to go into too many technical details, but as I said, we have 2 parameterization, one for the underwater structure, and so we have the drag force of the monopile or the jacket, or even of the floating platform. And in this case, this drag force is a function of a drag coefficient, which is usually unknown, the area faced by the flow and the flow velocity, and the number of turbines that we have in one model cell, which is in this case is usually one. So this is the bit that is introduced in the momentum equation in FECOM as a retarding force, and then the loss of mean kinetic energy due to the structure-induced friction is then included in the turbulence equation as a production term and as a source term in the dissipation rate equation as well, scaled by another parameter C4, which is also unknown. I will not go into the details of the equation, but just to say that there are two parameters that we don't know. And we were try then to tune those parameters using the data that we collected in 2023 and 2024. And I will show you something about this later. Then, as I say, there is another component that is the wind wake. So the reduction or acceleration of the wind in the wake of the wind farm. In this work, we are using a very simplified approach, and we just built a wind wake considering a maximum relative deficit and considering a length of the wake. We don't include any dependence on the atmospheric stability or number of turbines or any interarray effects among turbines. So it's a very crude parameterization, but it was just to start and to integrate all the different elements. And yeah, now I'm going to show you some results. This work, the wind wake parameterization was mainly done by Arianna Zampollo and Rory O'Hara-Murray in the Marine Directorate of the Scottish Government and in the University of Aberdeen. But I will not show any results about this yet. Instead, I wanted to show you some results about the effect of the underwater structure only. These are some figures about the seasonal changes, and in this case I'm showing what is happening close to one wind farm, which is the Sea Green wind farm in the Firth of Forth, and then we plan to extend these simulations to the wind farms everywhere in the North Sea. But we started with this one because we have data close to the Sea Green wind farm, so we are able to compare our model results with some data. In this slide, you have some seasonal averages of the changes in ocean surface temperature, ocean bottom temperature, and potential energy anomaly, which is a measure of the stratification. So what we found out is that over summer, these are the months of June, July, and August, having a wind farm, just the underwater structure, so without considering the wind wake effect, basically generates a decrease of sea surface temperature, which is about, on average, it can reach 0.3 degrees really in the vicinity of the wind farm. And then we have an increase in bottom temperature, which however is quite small. It's around 0.1 at the maximum, also very close to the offshore wind farms. And overall, since we have a sea surface temperature that is decreasing and bottom temperature that is increasing, it means that the density of the water becomes more similar in between top and bottom. And this means that the stratification is decreasing. But it's a very small effect, and But as I said, we want to know if this then has some cascading effect on the primary productivity, phytoplankton, and then fish, seabirds, and marine mammals. And this PEA is just a measure of the amount of work that is required to completely mix the water column. What we found out is that in the different months, we have slightly different changes. In particular, so these are monthly changes. So in May, the effect of having the wind farm there is almost negligible. So there are almost no differences in sea surface temperature or bottom temperature. Instead, the biggest changes are visible in June. They can reach up to half a degree, and also for the sea surface temperature, and is around 0.2 for the bottom temperature. Unfortunately, we went to measure, we didn't know this when we decided our ocean survey. So we went and measure temperature close to the wind farm in May, and that's probably why we don't see any almost detectable effects of the offshore wind farm. Instead, probably June would have been a better month to measure it. But this is something that we learn in the project, and this is also why it's good to use models to decide where to go and collect observations. And these are instead the averages for July and August. And again, you can see some effects of the offshore wind farms. They are not as large as June, which was the month with the largest differences. And they are about 0.1, 0.2, and slightly smaller for the bottom temperature. So as I said, in Pelagio, we wanted to go and measure the effects of having an offshore wind farm there. And we deployed some moorings with current profilers. We deployed some CTDs. We were there with the ship, and we made quite a few CTDs measurements, and also we deployed some gliders, but the gliders were not flying close enough to the wind farm to detect any changes related to the wind farm, but it was still good to have those measurements to understand if the model was getting right the baseline conditions. And as I said, we used CTDs, gliders, moorings, and one of the lesson that we learned is that we should use the models. We should run the models first to optimize the observational campaigns. We didn't do this here because the models were not ready yet to simulate the effect of the offshore wind farms. So we didn't go. I would say that we should have chosen a different month and slightly different locations, and maybe we should have maybe, yeah. We didn't choose the best location and the best time period to collect observation, but this is something that we learn and something that lead us to think now that we should use the models before designing an observational campaign. These are just a couple of CTDs profile versus different model simulations. As I said, these were collected in May, so we don't have a massive impact of the offshore wind farm, but still the impact, as you can see in the figure, is it's less than 0.2 degrees in terms of the sea surface temperature, and this is the location of the CTD. And just to say, 0.2 is small and is basically within the model error. So it's very difficult to detect in the model, but still was useful to have an understanding on how the different parameters I was mentioning before, CD and C4, have an effect on our simulations. And it gave us a bit of an understanding of the best parameters to use. This is another CTD. I'm aware that there is a bias in between the bottom temperature that is observed by the model, that is observed, and the one that is simulated by the model. But again, this is a difference that is about 0.1 degrees, which is something which is extremely small for an ocean model simulation. And this is, I will not go into the details of this, but this is just to say that CD and C4 have an impact, but it's not the range of values that we tested is not a massive difference. And using like 0.63 for CD and C4 equal to 0.6 is a good choice, and this was the same values that were found in state-of-the-art literature as well. And just to conclude, so basically we built all these models, so integrating the effect of the underwater structure. We tried to validate the model simulations with data in order to get confidence in the model simulations. We are going to use also the wind wake effect, but basically what we want to do, and I don't have anything to show yet, but it's going to be the main result of this project, is to simulate all the offshore wind farms everywhere in the North Sea. And then we want to compare the cumulative impacts of those offshore wind farms with the natural variability of the system and with climate change. And this is because we want to understand what is the acceptable threshold of change. Because if we are putting a wind farm at sea, we are perturbing the environment. But it's necessary to compare those perturbations with the natural variability and with climate change to understand if it is acceptable or not. And then we can use the models also to understand what are the best locations to maximize the energy extraction and to minimize the impact. In these 4 figures, you have present climate stratification, the natural variability, and then here I've added again the changes in stratification due to the sea green wind farm. So if you compare, in this case, the changes that you see here with the natural variability, more or less, the changes that are induced by the offshore wind farm are the same order of magnitude of the natural variability of the system. And the natural variability means how much the stratification changes from one year to another, because it's not always the same. And to calculate this natural variability, we need multi-year model simulations, and likely we have a 30 years model run that we did with the Scottish Short model. So we have this information and we can compare the 2 results. And then we want to compare the changes of the cumulative effects of the offshore wind farms everywhere in the North Sea with the changes induced by climate change, because also climate change is going to impact the stratification and mixing. So we want to see if the changes due to the offshore wind farms are larger or smaller than the effect of climate change. And this is my last slide. So just some take-home messages. So offshore wind farm can perturbate the natural equilibrium between mixing and stratification with changes in nutrients, oxygen, and phytoplankton distribution. Those changes can have cascading effects on habitat, biodiversity, fish, seabirds, and marine mammals. And we need to understand the acceptable threshold of change, comparing with natural variability and climate change. And so observational data are usually limited in time and space and cannot be used to predict changes before the offshore wind farms are installed and operational. So that's why it's important to have models, because we can predict the effects before the wind farms are built. But observational data taken in the vicinity of existing operational wind farms are needed to probably calibrate the models before we are going to be able to use them. I think that's everything. So thank you, and happy to get your questions.
Lovely, thank you, Michela. It looks like we already have a couple of questions coming in, so I will just pop this down and then we can have a look at the Q&A. So someone has said, fascinating research. Is there an obvious difference in impact between floating and seabed mounted structures? Could there be an engineering design solution to reduce the drag induced by structures? And is drag a key factor in affecting stratification?
Okay, very good questions, and something that we might be able to answer in the near future, but not now. So first of all, the simulations that we are doing right now are considering only fixed structures. The parameterization that is built in the model can be used for simulating also floating wind, but we didn't do any simulation with floating wind yet. And this is actually the objective of a different project, which is starting now. And so probably in the future, we're going to be able to compare the effect of floating and fixed structures. And yeah, the drag coefficient is important. And yeah, it's a key factor, but what we want to compare and understand it is if the structure, the effect of the underwater structure and the drag is smaller or larger than the effect of the wind wake, because we have these two components. So this is something that I'm looking at right now.
Great. Well, yeah, hopefully that person will be able to check back in as the rest of your research goes on. We do have another question, and again, not sure how much you'll be able to answer, but kind of as best you can. What are your predictions for the results of your research? Will the impacts be negative? Will there be a big difference in sea temperatures due to mass wind farms? Understanding that they're not available yet, there will have been some sort of hypothesis or directional belief at the start of the research.
We don't know, because we didn't analyze the simulations yet, and there was no directional belief or anything. So we just built some scenarios. So for the climate change, we are considering the worst case scenario, which is the business as usual one. And then for the offshore wind farms, we are considering all the wind farms that are planned to be in the North Sea by 2050. But we don't know yet if we expect to see some changes in stratification due to the offshore wind farms, but we don't know how they compare with the changes due to climate change.
Okay, great, thank you. I wondered, obviously, there's kind of the political will at the moment to increase the energy that we're getting from offshore wind farms. Do you find that there's any challenges in communicating this sort of research, or even getting funding to do this sort of research in that context?
Okay, in terms of funding, I think in the last 3 years, I mean, the EcoWind program started in 2022 and is funded by NERC, and then there is a continuation that is called EcoFlow. So there was actually influx of funding for research around offshore winds. In terms of the communication of our results as evidence for policymakers and things like this, I think we are not there yet, but also because we don't have some final results, as you have seen also in my seminar. Still, I don't have some final results saying, okay, this is good, this is bad, but I expect that one of the main things that you're going to be able to provide in the future is, for example, saying what are the best locations where to put the wind farms and the locations to avoid, or also if there are some thresholds that we should avoid, like, okay, it's okay to have 3,000 turbines, but no more than that, something like this. So the research that we are doing can actually be useful for the expansion of offshore wind in a sustainable way. We don't want to stop it, but we just want to do it in a way that is non-detrimental for the environment.
So the attendee said, thank you very much for your great research. The first part of their question was, what is the characteristic current speed in the OWF region?
But it's about, I think I have it. 0.5 meter per second maximum, more or less.
So the second part was just, is C4 also related to CD or independent? And then does CD and C4 remain constant in all conditions?
Yeah. So CD and C4 remain constant in all conditions. Maybe possibly we should change at least CD to be dependent to the speed velocity, to the speed of the currents, but we are not doing that yet. And they are independent. They are two independent parameters.
And the next one is the degree of effect on a large enough scale that restrictions should be introduced into planning legislation?
And this is a good question. This is what we want to understand with simulations that we are doing with all the wind farms everywhere in the North Sea. So from the simulation just of the sea green wind farm, which is just one wind farm, the changes are not very big, but potentially the cumulative effects of all of them can be relevant. So this is something that I should be able to reply in the next 6 months, probably.
And then finally, has any similar research been taken around oil and gas platforms, or are they more widely dispersed and less likely to have a cumulative impact?
Good question as well. No, there was no research done around oil and gas platforms, even if they are structured at sea and they have a drag. And yes, it's true, they're more dispersed, and probably the offshore wind farms we are going to have thousands of them, and I don't think we have thousands of oil and gas platforms. But yeah, that research was not undertaken for oil and gas.
Okay, thank you. That's interesting to know. It looks like that was our last question for now. Thank you, Michela, for presenting. That was a really interesting webinar, and obviously we've had lots of engaged attendees, so hopefully that Q&A was helpful for them as well. That's it from us today. So thank you everyone for logging in, and I hope you found that beneficial. If you are an IES member, then please make sure that you record your attendance at this webinar in the IES CPD tool, which you can do on the members area of the website. If you're watching this as a recording, please do subscribe to the channel, like this video, and click on the bell icon to be notified when we share new content. So just another final thank you to Michela for presenting, and thank you to everyone for logging on. I hope you have a lovely rest of your week. Bye.